Homework 10 is on the web. I got maybe an email from the system saying that it was, what did I do? That's due next Wednesday. It's about correlation and regression. So the stuff we did on Monday, what we'll do today should be enough to look at that. Friday and Monday, of course, are the Easter holiday, so that's why it's due then. So today we'll talk more about correlation, look at some plots and some data. And a test of whether the correlation is 0 or not. Because often you're looking at variables and you want to know, is there a statistically significant correlation, or is this kind of apparent pattern we see, maybe just due to chance, that it's not really there. There's a lot that could be done with regression and prediction. We'll look a little bit about transformation. Sometimes you can change things on different scales, and things will be more linear. Part of that message is look at the data. See what's there, even if it looks like there's a very strong correlation or significant relationship. You still want to look at it and see what is going on, and some examples of some things. But any questions before we go on? So correlation. Measures the strength. So it measures the strength of linear association. Between two quantitative variables. So looking at correlation, it measures that. We're going to have data on where X and Y are measured on pairs. It could be you measure both X and Y on the same person. So you measure blood pressure and heart rate, or body mass index and blood glucose. So you have two quantitative measurements on individuals. Or maybe, a matched pairs experiment, you could do this person and that person and measure them up. And our measure is, the big full name is this Pearson product moment. Correlation. That's there, one representation of it. And you'll see different, whether you multiply things out or expand on something, it's called R. 1 over n minus 1, and over all of our pairs, we're going to add up xi minus x bar divided by the standard deviation, kind of a standardized x score, times the standardized y score. This is how it's computed. We won't really be computing it by hand, but that's what it is. This thing turns out to be lies between -1 and 1. When it's 1, it's perfect straight relationships. If R is pretty high, 0.8, 0.9, you're going to see a pretty strong, relationship in there. If it's negative, right, then it's sloping down. There's a negative association. As X gets big, Y tends to go down, and vice versa. So if it's sloping down and a little bit more spread out, maybe the R would be about -0.6 to kind of sloping down, a little bit less tight around that line. Just a couple examples of these values. R near 0, right, is basically no linear association. R is about 0. You could have points that are just kind of all over the place, right, between X and Y, and not much of any relationship at all. You might have kind of an up and down relationship. It might kind of go up for a while and then down. So there could be some pattern here, but it's not all up or all down. It could be kind of more diverse. And you could have some funny things, you know, that you could have a bunch of points over here, and then a couple points kind of over here. And you know, if it's kind of level there, it's not really going to go up and down. You don't necessarily know what's happening in the middle. It could be a strong relationship, steeply up or steeply down, or something like that. So a number of things could be no apparent linear association or relationship. But the other cases, if it's closer it gets to 1 or -1, the stronger it is. So I wanted to look at a few just examples and some data of examples there. But as we've been doing in inference, there's usually a population, and so there's kind of a true or theoretical or population value. So the population correlation is usually noted by the Greek letter rho. It would also be between -1 and 1. R is our sample estimate. And if we wanted to test, is the correlation equal to 0 or not? There is a command in R called correlation test, core.test, where you put your x and y's in there. And what this will give is a t statistic. And it will compare that to a t distribution where the degrees of freedom are n-2. And if your t statistic is very large, then you're going to be near 1 as a correlation. If it's very small, the correlation is at -1, then the t statistic is going to be very, very small. If you get a large sample size, it can still be a big t statistic, even if you're not so close to the edges. And depending on the t statistic, we're going to reject the null hypothesis that the correlation is 0. So this is the population has no association between x and y. Too much static. We're going to reject H0 if our t statistic is large, for the absolute value of it. And we'll see that in some examples. There's a formula in the book for calculating that. And so you can reference that and use that at least in one problem. But let's look at an example. Does anybody have a copy of this handout? I think everybody. Yeah, that's good. So as a first data set, we're going to look at something that's in R. Right? There's this data set on arrests in the United States. It's a data set about violent crime rates in 1973 as they vary by state. You can reproduce these data for modern era probably with a number of other things. Right? And so it's 50 observations for the 50 states. And it's murder rates, assault rates, rape arrests per 100,000 people. So these are in small numbers, and also percent urban population. And so for instance, the murder rate, if you look at a graph of it, oops, I made these plots. These are the histograms of the assault rates. People arrested, 200 per 100,000 people. Right? Murder is much less, 10 per 100,000 people, and so on. Right? Some examples. Right? Murder and assault. Right? So these are two different variables. Right? If you plot them, they look like this. Right? There's 1 point for every state, so murder rates and assault rates. How would you describe this relationship?
Strong, positive.
Fairly pretty strong positive. The correlation, if you compute it, this command here computes that correlation, that R value is 0.8. That's an example with 0.8. The relationship between the arrest for murder and rape, that's the plot. Does this look stronger or weaker than the other one? Looks a little bit weaker, right? That looks kind of more conforming to the pattern. This has a little more variability in there. The correlation is actually 0.56, so it's going down a little bit. The murder rate versus percent of the urban population. Not a whole lot of distinct pattern there, right? There's a little bit because it's kind of lower in both murder rate and urban population down here. So that's enough to make it a little non-zero, but it's 0.07 rounding it. Practically zero. The correlation test thing then asks, is there a significant association? And between murder and assault, right, do you think there's going to be a significant association here between the variables? Correlation 0.8. This is what the output looks like. It tells you it's doing that our particular correlation. T-value ends up being 9. Right? Any t-value is much bigger than 2 usually are significant. Right? 50 states, so it's comparing to a t-2, and it gives us, this is a scientific notation for very, very small. Right? It actually gives a confidence interval for the correlation. You have 50 states, it's pretending it's a sample of 50, right? And then doing a confidence interval for that. So this one clearly is non-zero. Murder versus urban population, well, let's see, we can do. The next one was, that was a little bit arrest rates. 4.7, very small p-value, confidence interval here clearly bigger than 0. So that's highly significant. The t-value is not quite as big as the other one, but still is still significant. Versus urban population, right? This picture, the estimate is 0.7, confidence interval negative 0.21 up to 3.4, t-value 0.048. That's not, very extreme, and p-value is not significant. So, we have 50 points. There's a little non-zero correlation in the sample between urban population and murder rate, but it's not statistically significant if you're thinking about this as a sample of 50 points. The rest of the handout, we won't go through everything on there just because of time, but you could follow through on these if you wanted to see some. There's air quality measurements also from 1973. Pairwise, so what is that? Look at a few of these rows of this data set. These are measurements in New York City, so ozone, solar radiation, wind, temperature. These are the quantitative measurements. We'll skip month and day on this. If you look at correlations between pairs of variables, some of them are negative, like between ozone and wind is negative. You get more wind at ground level, and it blows the ozone away. Right? If it's stagnant, then it stays there. There's a positive association with temperature. As heat comes down, sunshine, the carbon or the chemicals coming out of exhaust from cars react with that and start forming ozone. Right? So the heat and the sun, right, do that. So higher temperature is associated with there. Right? If you do, so temperature versus ozone is positive. How would you describe this relationship? Pretty strong. Right? A little anomaly in here, right? A couple days that the temperature was kind of high, but the ozone was kind of extra high for some reason. So you might be interested to know if that was a weekend or was that a work week or something going on. Was the wind particularly low that time? Kind of other factors there. If you do the ozone and wind, that's what it looks like when it's a negative slope. There's kind of something going on here because ozone doesn't go below 0, so there's a bound there. So it's like it's kind of sliced off. That's the limit. That's negative correlation. That's there. If you want to test, is there an association between temperature and ozone? Yes, there's a very high significant one there. Temperature and solar radiation. Yes, wind and solar radiation. Not so much. If we did a plot of wind and solar radiation, pretty random. Right? not necessarily seem so. Solar radiation is emissions of sunlight and the wind. They have a correlation that's slightly negative, but not significantly different from zero. So you could do a number of things with correlation. So in many studies, if you're interested, you're measuring things on people or medical conditions. First analysis might be looking at a lot of plots. You're taking blood chemicals on people, different concentrations of chemicals or hormones or things. In measurements, you might have dozens of variables, and you're looking for the ones that have the highest correlations. Let's see. So that's what we're doing with correlation. But any questions about it? There's a lot of extra little tidbits in that chapter. If we had another semester, we would spend a little more time on that. And maybe sometimes this book has a lot of technical things to it. It would be a useful resource if you're taking a second class or reading articles. So if you're looking at other examples. The second topic that I think is interesting to look at is transformation. And thinking about that sometimes there really is a relationship there, but it's nonlinear. So imagine you had some data that X and Y, and the data you saw was a pretty strong relationship, but it was curved. Let me just draw a curve, a quadratic curve up here, and maybe see your data kind of around this somewhere. There's a little bit of variability here and there, but it's curved like that, right? If you calculate a correlation, this is going to be pretty high. Right? It's still going to be a correlation 0.8, something 0.9, because generally there's pretty much of a straight up increasing pattern, but it doesn't fit really. It's not really describing what's going on. If you fit a least squares regression in here, right, we draw a line that goes something like that. The one way we could look at that, the fit of the data, does it seem linear? Besides looking at the value of correlation. Yes, it has high correlation, that's good. Yes, there's generally a positive association. If we take the y minus y hat, and the predicted values, the y hats are the y's, the y levels determined by the regression. And if we plot that versus x, right, so we're calculating these distances in here, the distances from the x values to the regression line, these vertical distances. These are the little e values, or those distances plus or negative. In our linear regression, those are going to be centered at 0. So line here. So what do you think the pattern's going to look like if you plot it on that scale? So if you have some points out here. So there's a lot of kind of positive residuals at this end. And there's some positive residuals at this end, typically. And in the middle, there's these negative ones. So you're going to get this funny, this residual plot. You get some positives over here, and then some negatives, and then some positives. So it could suggest that the relationship is not really linear, but there's actually a curve to it. Some things, like the relationship between radius and area is a quadratic relationship, right? And some things in terms of size or distribution in species are not necessarily exactly linear. So if you suspect there's something like that, maybe by thinking about the biology or the application, there might be a rationale. Engineering, chemistry, there might be nonlinear relationships, right? And so one thing you can do with this, in multiple regression, we're not going to cover this, but in multiple regression, if you thought that the data really were, you can have different coefficients, and you can have an x in here, and you can have an x squared in here, plus an error. So you can actually do a model that really does that quadratic thing and match your data well. That's one possibility. Another is sometimes some transformations can put things on scales that work better. So let's say our y is actually an alpha, e to beta x. Say it's really that kind of quadratic exponential model, if that's really what describes its nature. If you plot x versus y, it's not going to look linear, right? It's going to take off as x gets big. And if this beta is positive, as x takes off, y is going to shoot through the roof, right? So it's not going to look linear. However, if you take logs of both sides, right, the way logs work, the log of this side, the natural logarithm, the log of a product is the sum of the logs. This is how it works mathematically. And the log of e to a power is its natural log, then is just beta times x. So what you end up with is that this log variable versus this one is a linear relationship, that it becomes straight. So linear on a log scale. That happens. There could be a number of other examples where you could write down mathematical equations by taking logs or square roots, ends up making it look straight. Rather than do a big treatment of that, let's look at some examples. Kind of an underlying message of this as well is that you can look at your data. As you look at your data, right, then you see patterns, and then it could give you some insight into what's going on. So on the handout, then there's some data there. This is data. This data set is called brains, right? Let's see, how brains that? No, it's from a different source, right? So here's 3 measurements that are in this brains data set. Plot brains of body weight as an x variable, and then the brain weight of, this is what the data look like. So what these are is they have a number of species, the number of rows of brains. There's 62 mammals, and they've taken a sample from each one and measured the body weight and measured the brain weight. Why would you do this? Well, if you're studying relationships among different types of animals, you might want a lot of physiological measurements, length of arms relative to this part of the arm, relative to the length, to the torso, different sizes of internal organs and things like that. And if an animal has died, you can take accurate measurements of the body, the brain. They've done it for 62. So you imagine your situation, you have a new animal, right, that's still alive, and you want to have some idea of what the size would be predicted, right? Does it look, right? So you wouldn't necessarily want to kill it, but you can easily measure body weight, put it on a scale, and then try to predict brain weight. So these are the ones, right? There's a few, these are in kilograms. So there's a few pretty big ones. What do you think the big animals are? Yeah.
Elephants.
Yeah, a couple elephants. There's an African elephant and an Asian elephant, I believe. Right? There's other ones that are pretty big. So 1,000 kilograms is a lot bigger than us, right? But there's cows and horses and hippos in there, but there's a lot of them that are quite small, right? Does this relationship look, do you think there's a high correlation between these two things? Does it look kind of straight? Right? That when it's like this, the correlation is going to be really quite straight. So there's 2 variables there, so I can just type the correlation of it, and it will give me the correlation is 0.93. That actually ends up being a very high correlation. But there's a little bit of kind of a little curve in there, right? You can almost see it. And maybe there's something going on, like the brain weight is a certain percentage, or maybe it's the cube root of body weight. There could be some biological relationship that's not exactly straight. If you take the log of both of these things, well, the other thing that's going on is there's a few giant, very large cases, and a few, and most of them small. So there's kind of a big range of this variable and a big range in this variable. If you plot, plot log of the brains, the body weight, versus the log of the brain data set, the brain wave. This is the picture you get. The log takes the very large animals, and they're not as far away on the log scale. It's kind of like the exponents are not so much different. And it happens for both the brains and the bodies a bit, but not as extreme. But the log of both it looks pretty straight, right? And you can see it and confirm it. And although we had high correlation before, right, the correlation here is a little bit higher, 0.96. It was 0.93 before. So that, if you looked at it and had some idea that maybe it's not exactly linear from science, you might then take the log. So say I have an animal that weighs 100 kilograms. The log of that is 4.6. 4.6 is about here. I could do a prediction on the log scale, and let's say my prediction is about 4.6 here. It's about 4.6 again, something like that, or 4.5. On the log scale, to get back, exponential of 4.5 going back is about 90 grams for a brain weight. So there's a way, after you transform it, if you did prediction on that scale, it looks better for the linear assumption. It probably will work better. Right? It doesn't look like we're making such a drastic jump. Right? If we fit a line here and had to predict for something in the middle, it's like a drastic jump. And it looks a little unsettling. Right? You would kind of be worried about it. This, though, there's kind of a nice support all the way along and a line that looks reasonable across the whole range. So sometimes these things straightens things out, and it works well. Another example where in which this happens is some measurements are in distance, some are in area, some might be in volume. So as you square and cube things, you get these nonlinear relationships, right? And Stephen Jay Gould, in addition to being interested in science, was very interested in baseball and also churches, so in architecture. So Weisberg is a applied linear regression book. There's a data set in there about measuring the perimeter and area of Romanesque churches. So you think about a perimeter, right? It's the distance around. Right? So if it's a square, if it has a certain distance on a side, the perimeter is 4 times the side. Right? But area of a square is the distance squared. Right? So if you plot perimeter versus area, you might get a nonlinear relationship. Right? You might get this quadratic. Right? And you do, and I'm not sure that I have that data in there with that. But anyway, this is the perimeter versus area that's kind of increasing like this. And yeah, that's kind of subtle. There's a little subtle curve there, maybe. Based on the physical measurements, area versus distance, we might suspect there's a nonlinear relationship. This residual plot thing kind of gives a funny pattern with a bunch of before and a couple sticking out there. Now, if you take the square root of area, right, take r squared and take the square root of that, that's back to the original distance, right? This one looks nice and linear for all of these two. Right? And also kind of easier to see that there's these two that are kind of sticking out. Maybe these two largest ones have something else going on. And once they get to a certain size, they are growing in size in a different way. The residual plot looks kind of funny, there's just two kind of sticking out there, but the square root of this one variable shows you something a little bit different about the pattern. I think Notre Dame was made well before these Romanesque churches, so it might not have the same pattern, but there's not as many churches from that time. So, but anyway, so sometimes looking at your data, even if there seems to be, right, that's a pretty good correlation, right? But there's a little bit more to it by looking at it and thinking about it that you might see. So, right. But any questions about? Well, let's look at a couple kind of problem examples, right, and see what we can get out of that. as further examples of thinking about regression. So that's the transformations there, here's the combined. Here's a couple of problems that are included there in the, so here's a problem. Mendenhall and Senich is another introductory statistics book. It has this problem from Journal of Biology on sport. So they took 8 high-level Olympic male water polo players, and they studied things relating heart rate to oxygen uptake. Right? And one set of measurements was a heart rate percentage. So during some 8 different quarters, what the mean heart rate over 4 quarters of the game. Maybe they had monitors on them. Maybe they took at different points, right? As a percentage of some maximum heart rate, right? So maybe they had these individuals do a very strenuous exercise and see how much they can pump their heart rate up. Maybe it's safe for them because they're at this level of competition. You wouldn't want to do it with people that have any risk of that. And some maximum oxygen uptake. It doesn't exactly say how that is measured. Right? So the X and Y, and you get this output here. This is in Minitab. It's a program, right, for computing computation. And the type of questions that would get asked from this is, what's the regression line? What's our equation for prediction? So this here, right, is where it gives it. But the coefficients are also expressed in here. R and other programs will use slightly different words. Right? So you don't want to get too tied to looking for only specific words. But you want the general, it's always the same pattern. So instead of constant, R calls it intercept. By negative 27.24, and then plus 0.558 times x is the equation for predicting. And so if you had somebody where x was, say, 160, so x is 160 is this maximum heart rate uptake there. The predicted value is calculated simply by putting 160 in for x. And calculating that out, that becomes the predicted value on the regression line. Now, in an individual's point, it could be above or below that, but that's the prediction. What's the difference if somebody has, say, 170 as their oxygen uptake? Somebody has 10 points higher on oxygen uptake. What's going to happen to their heart rate percentage? It's going to go up. Yeah. The slope is positive, right? So the y hat here, negative 27.24 plus 0.558 times 170. Right? What's the difference between these two people? What's the difference between these two people? Well, you can calculate both of these things, right? You take the difference, but where is the difference affecting? It's affecting things here. That coefficient times that thing that's 10 different. So I can tell you right now that the difference between these two things is going to be 5.58. Because instead of 160, I multiplied by 170, so it's 10 more. So the average difference, 5.58, comes in there. So it gets used for that. But there's this extra stuff here, right? So we can do some hypothesis tests. Yes?
So you got that average difference from the oxygen coefficient?
Yep.
So you multiply it by 10, basically?
10, yeah. So because it's 160 versus 170, that change of 10.
Oh, okay.
Yep. So in this, so our first example, we'll put a couple notes in here. The water polo. The x versus 160. 160 versus x equals 170. The slope was 0.558. So the expected difference in y between these two individuals is simply the 170 minus 160 times that the rate of change. So 5.58. You might be more interested in that slope. So often in regression, you take a little more attention to the slope there, and either do a confidence interval for it or do a hypothesis test about it. So the hypothesis test for the slope, the null value is just that it's 0, no slope, and no association. Which means x and y are not changed together, and it's just this random pattern. The alternative is that there is that it's not 0, but there is an association, and that it's statistically significant. The testing for this, the t-statistic for this test, is just simply the coefficient over standard error. The formula is in the book. You won't have to calculate it directly. We just read it from the output. And so this one, the coefficient 0.558, and then the standard error 0.113. The t-value is 4.94. In this, that seems pretty big. N is only 8. Degrees of freedom in regression is n minus 2. We take away 2 because we've estimated the slope and intercept. We've estimated the two coefficients for that line. And so that effectively uses up a little bit of information. And so we're going to reject the null hypothesis if our t-statistic, the absolute value of it, is greater than a t-distribution with 6 degrees of freedom and 9.5 cutoff. That's a pretty bigger than 1.96. It's a bigger value. So over here, the quantiles for a T975 with just 6 degrees of freedom is 2.45. So we got to be bigger than, if we're bigger than 2.45, we will judge that there's a statistically significant relationship, right? That our estimate, the slope, is several more than enough standard errors away to convince us that it's not actually 0. So in this case, right, we're going to end up rejecting it. So here, reject H0 because our statistic is big, 4.94. And so that's pretty much incorporated there into the analysis. I think it's a p-value that's 0.003. That's very small, so you could look at it that way too. Any questions about? Sometimes you want to do 95% confidence interval for the slope, right? Where are the likely values of the slope? It's the estimate plus or minus our t-value, the degrees of freedom, and then 0.975 times the standard error. So a lot of the confidence intervals I try to represent as estimate plus or minus a distribution value times standard error. This fits the same pattern. If we wrote out the whole thing, right, these are slightly more complicated things, but it would be the 0.558 plus or minus 2.45 is our cutoff value. Right, that's where that one comes from. And the standard error of 0.193. And that wouldn't include 0, right, because that is significant. Any questions? The other things that are in that output that are worth noting a little bit, there's this R squared value that's this output is RSQ with 80.3%. As a decimal, it's 0.803. So R squared is the percent of variability in Y. Explained by the linear structure and X. People often talk loosely that it's percent of variability of Y explained by X. It's not necessarily really a causal thing, right? Because in this case, you can't really probably increase their heart rate, independently of their oxygen consumption, right? If you can train somebody so they're healthier and more efficient in terms of muscles and everything like that, better condition, then probably both of them go up. So it's not really causal in that sense. In an experiment or an engineering context where you can manipulate input factors, it might be more causal. This R squared is this typical measure that's saved on as a decimal. It's between 0 and 1, so 80% is pretty good. And there's an S here. Before we call it S, it's an estimate of the standard deviation. And what on that sheet there's a 5.27. And this is, that number there is related to spread of the residuals. Y minus Y hat. So it gives one more piece of information about how accurate the line is. If this is small, then you're really close to the line. If it's big, you're further away. Yes?
Is that S times E or is that standard?
It's like a subscript for E.
Oh, okay.
There's not really it's a standard deviation of the residuals. So it's not, across textbooks and introductory books or more advanced books, there's not really one notation or one terminology for this. So in this data set, if you, a couple pages after that handout, this R code, we won't go through it all, but these are the data. This is what the plot actually of these oxygen versus heart rate actually look like. By correlation, 0.9, pretty good, right? There's some commands in here for actually computing the, we're not going to go through all these in detail, but those are kind of the intermediate computations. The regression line is there. And that value of S, that value of 5.2, describes the variability in these vertical distances. And this little loop thing here is making these little lines. These are the residuals. These are the errors. And if you look at these scales, this big one here is about almost 10, right? This one might be about 8. This is two separate ones, one positive, one negative. Other's about 5, V2. That's a small one. And so the standard deviation of those vertical distances is about 5. Right? So that describes something about how close the points are to the line. If the standard deviation was 1, they'd be, they'd all be like this one or these couple. Right? If the standard deviation was 10, they'd all be, there'd be a bunch of them that would be further away. So it gives you some information of how it does there. Right. Let's look at one more book problem example and an issue that comes up with regression and why it's important to look at your data. So a number of years ago, professional baseball expanded, and the Colorado Rockies started playing. They play in Denver. Denver is at a mile of elevation, 5,200 feet, right at the highest mountains in Vermont are about 4,000 feet or a little bit more, so the whole city is up there. Right? And as you go to higher elevations, there's less atmosphere above you, so there's less pressure above you. And so in baseball, you want to hit the ball and make it go far. Right? And so if there's less air pressure pushing down, maybe it flies farther for the same hits. Right? So in the 2003 season, there were 29 cities with major league teams. These are they recorded the elevations for the teams and something called slugging percentage. And this has to do with hitting longer distances. Right? Do you hit to get one base? Do you hit a home run? Do you hit to the outfield? I'm not sure how exactly it's calculated, right? But higher ones would be better. Right? And so Denver was pretty high, 0.625. And so is there an association between elevation of the field and the slugging percentage? Right, so here's a plot, right, of it. Here's the up to 6,000 feet. Here's the slugging percentages. And this one's Denver. Do you think there's much of a correlation there? Is there much of an association, right, between elevation and slugging percentage? Well, we could do a little bit of work. Let's see. There's a data set. These are the data that's actually from that article, Chance magazine. So it's the city, slugging percentage, and elevation. That's there. We can read that. LS, is it in here yet? No, it's not in there. So list.files lists the files that my directory is looking at. So it's looking at that and it's there. So I can just do MLB is, I can read that thing in. MLB parks, CSV. And there is a header. There's a row up there to tell you what it is. So when you read that in, you get the data. Here's the data for all those teams. There's something, so if you just plot MLB with slugging, no, elevation is the X variable, and MLB with slugging percentage, there. Oops, no, it's just slug. Right. Oops, what is it?
Elevation. Capital as an L or no, not an L.
Elevation, okay. Right. That's the plot that's in there. Right? When you do regression and one variable is on a very different scale than the other one, the coefficient, the slope coefficient has to go between the two. Right? So the slope coefficient has to take things in the thousands and take it down to decimals. So you're going to get a coefficient there like 0.00005 or something. It has a lot of decimals in it. So one thing you can do is change the scale. So I'm going to multiply all of these by 1,000. Right? So a 50% slugging percentage is going to become 500. Right? And the ones and so on. And baseball often talks that way in terms of batting averages. You multiply everything by 1,000. And so if you do that, then I'm going to attach it so it's easy to do those. Now when I do this plot, see it's the same shape exactly, but the numbers are more comparable. So what I do, when I get a coefficient, it's not going to be such a tiny, tiny decimal. Right? That's the plot here. Right? The correlation between these two things is 0.485, and if I do my correlation test, it's statistically significant. Here's the t-value, p-value is very small. The confidence interval for the correlation clearly doesn't include 0. So it looks like there's a statistically significant correlation. Do you believe it? Are you willing to go out and say that's why they're doing better, is that they have this elevation, it's helping their team, that's why they have this better slugging percentage. A little skeptical? So in this point, in regression, it's called an influential point. It has a lot of leverage on it. If you actually plot the regression line, it's going to basically go through that point. right? So our criterion, our least squares criterion, is prediction in the y direction. Right? And if we don't match points, then we get penalized by the square of that distance, right? So if you put a straight line out here, right, then you get a big distance here, and that's going to be squared, and that's going to be huge. So instead, it's going to pull it up there. Wherever you go through the middle here, whatever the slope is, it doesn't change the vertical distance too much, so it's not going to care. So you can, let's see, if you put an AB line and you do a regression of the slug percentage, yeah, no, I just called it slug, as not percentage, as elevation. Right. Put that on there, that's where the line goes. It might not go exactly through that point, but in terms of the graphing capability, it looks like it does. Right? And so it pulls it up there. Right? If we define a variable to identify the low one, say less than 3,000 elevation, you could cut it at 4,000, 2,000, there's a big gap in there. And just call that low. So low now, right, it is a variable actually that's true everywhere except Denver. So when I do the plot now without Denver, just the low ones, it looks like that. Among those other 28 teams, that's what it looks like. The correlation without Denver is 0.19, so it's gone from 0.49 down to 0.19, right? Which is still, it's not zero, but we don't have a big sample size. So if you do the correlation test on those, all right, then the p-value is 0.3, not significant. The confidence interval for the correlation, -0.2 up to 0.5. Small sample size, so it's kind of wide. Right, so that one influential point really drives it, but you wouldn't necessarily want to base your conclusions on only that. Right? Once you look at the data and see that there's this one point that's kind of anomalous to the rest, you could run things, the regression or the correlation with or without it, and see how things change. Right? You could report both, right, and then let the reader decide, or you could make a suggestion one way or the other. It's a little bit hard to believe that it's just that if I do all the data, right, and do a regression, I still get kind of a small value. This is 0.02, right? That's what this as a coefficient here. And it's significant, it's statistically significant. R squared, this percent R here, our program calls it multiple R squared. It's just an R squared really with one predictor. If you had multiple predictors, it would be, what about 0.24? That doesn't sound too high, right? 24%. Not unusual, but it's statistically significant. If you just use the low ones, I don't know why that code is not in there. If you do the slugging percentage as a function of elevation and set the data to be our MLB data, but just the rows where that had low elevation, that's how you can just select those and then run it and then summarize that. The model just using the low ones, then you get this estimate of 0.02 as the slope. The coefficient is, the p-value is 0.33, not significant. R squared is only about 4%, 0.04, much smaller, right? And so by looking at it and thinking about whether you really have a linear relationship that you can believe in, or there's an outlier or an unusual point or something distorting, and you get a better picture, right? So if you had to make a bet whether there's really an effect of this elevation or not, not clear that there's something, right? There could be a lot of other factors, right? This is just 1 year of the teams, right? That maybe that team was really good that year in that dimension, right? Anyway, you might do the data collection better. Maybe multiple years. There's certain, yeah.
Including more cities.
If you could include more cities, there might be more now in the major leagues, so there could be a few more. There's kind of that gap. If you had some intermediate place, like in Utah, maybe wasn't, I know Utah was really high, Salt Lake City, but there were a few that were a little bit kind of intermediate in elevation, you could kind of check things, yeah.
I mean, you could use like the minor league ballparks because they're more impaired ability
Oh,
than
yeah.
they are.
Yeah. But they have, yeah, so if you had minor leagues at a certain level, right, they might, if it holds for the pros, maybe it would hold for them too, right? There's also kind of a, is it that team or is it the visitors to that stadium? You know, you get a much more complex data set there. There's certain players that specialize in hitting, pitchers, and other ones aren't necessarily the best hitters, and they bat in one league versus not the other. So there could be a lot of ways to get a little more specific, and maybe it wouldn't hold. Maybe it's just an artifact that Colorado Rockies are doing very good. That could do it a year. But anyway, it's easy to imagine that with a little bit of data and a little analysis without checking a lot, you can give a lot of news publicity about some phenomenon. A lot of people spend time thinking about it. But that's kind of what we're going to do with regression. You know, we might look at one example of multiple regression, but that's not that's a homework. So, any other questions about? All right, well, have a good Easter, and see you next week. Have a great weekend. Thank you. See you too. Bye. All right, bye. Yeah.
They do have this break. Oh, yeah?
Yeah.
Is that like what my son's been?
I still can't feel my feet.
See you. Have a nice break.
Yeah,
you too.
thank you.
Yep.
You want me to sit?
How you doing?
Have a good one.
Professor, enjoy your break.
You too. Thanks.
If you get in and I don't, I swear to God, Ian, I'm gonna be so